Okay, when we finished up the notes, we were talking about precision and accuracy. Now, when you report, if you're taking data, if you're recording numbers, there's a way of doing it because if I get data, I have to do calculations with it. So when we're doing data, when we're collecting data, we have something called significant figures. And significant figures are the figures that you actually measured to, okay? They allow you to be as accurate as the instrument that you're using. Here's an example. Okay, if I'm measuring this amount, this is a scale, so I'm measuring mass. See how it's 10.4. This is how I would write down my measurement. Okay, and I would have three significant figures. I went one past the decimal here. If I had this scale, which is more accurate, I'd write it down as 10.4977. Okay. And the reason I can do that is this instrument is more accurate than this one. And so these numbers are more significant. So then when I do a calculation, I can add more numbers to my calculation. For instance, if I do a calculation with this, if I'm multiplying, I can only have three what they call significant figures, and I'll talk more about those in a minute. On this one, I can have 1, 2, 3, 4, 5, 6, 7. So when you're doing calculations, you need to look at the number of significant figures. That tells you how accurate your answers are. See, the thing is, like sometimes you do a calculation and let's say you take 3.9 times 7.4 and you write down, 22.663974. You can't do that because what you're doing is you're giving an answer that's more accurate than the measurements you took. So it's important when you do calculations in science that you use significant figures. Okay, and again, sometimes when you're measuring like with a meter stick, if it has little marks in it, you can measure up to the where you think it is, and then you can estimate one more. So like if it's at 10.4, but it goes a little past, maybe you want to write 10.41. But you can't go 10.4977. You just can't do that because your instrument isn't that accurate. Okay? Here is the rules, and this is in your book for determining if a number is significant or not. Okay? So the problem is zeros. All non-zero numbers are significant. So here you have 3.45. All of those count. They're all significant because they're a non-zero number. If you have a zero in between two non-zero numbers, it's significant. So again, this has 3. Okay. If you have a number like this that's less than 1, this 0 is not significant. I can put all the zeros I want. It's not changing the number. So, but if you write zeros after, so here I write the decimal and I write 4, and then I wrote 2 zeros after, this has 3 significant figures. This one isn't, but these ones are. Well, you're like, what's the difference? Well, if you were taking a measurement, why would you take the time to write the decimal and 2 more zeros if your instrument didn't measure up to that point? They just happen to fall on 0. That's why they're significant. This one has 2 because I took the time. I mean, it's 4. But why would I take the time to write a decimal and a 0 if I didn't measure up to that point? So when you take your measurements, you write up to what your instrument tells you, and sometimes they just happen to be zeros. So you write them down. Okay. On this one, this is 6,000. Okay. See how there's no decimal? This is an estimation. Okay. So if somebody said, well, how many people were there? There was like 6,000. I didn't measure. So the only thing that's significant here is the 6. Okay. So if you're doing a calculation and you want to be close to the right answer, but you can't have that many significant figures, you can use zeros, just don't write a decimal. If I want all of these to be significant, I write down a decimal. So the difference between these two, 6,000 and 6,000, because this one doesn't have a decimal, it only has 1. Because this has a decimal, I measured up to that point. It just happened to fall in zeros. Okay. On this one, if you have numbers that are less than 1, you don't start counting until you get to a non-significant number. So all of these zeros are just placeholders. This has 2, this 4 and 0. Okay. On the same thing when you're talking about scientific notation, that would be 3. Those 3 would count. Okay. And again, this is in your book. You can read through it again. I know I went through it kind of quick. Sorry about that. Okay. So when you're doing calculations, okay, the exact numbers are obtained by counting. If it's uncertain, okay, if you have an infinite number of significant figures, that's why, again, when you use a instrument, you use the numbers that come up on it, and then when you do your calculations, you make sure that you look at the number of significant figures. Okay, I think I have that. Yeah, significant figures. Okay, when you're multiplying and dividing, all right, what you do is you multiply the two numbers together, and then you look at your answer. Your final answer can't have more significant figures than the measurements you took. So let's say I have something that has 3 significant figures and I multiply it by something with 2 significant figures. My answer has to be rounded so it only has 2 significant figures. Okay? And again, that's to make sure you don't report an answer that's more accurate than the measurements you took. Adding and subtracting is easy. It's the decimal. Okay? Like if you had 17.6 plus 3. Well, that would be 20.3 or 20.6, sorry. But because the 3 didn't go past, you'd have to round that up to 21. You can't go any farther past the decimal than the one goes least past the decimal. Okay. I should have some problems here. I do. I have a PowerPoint that I'll put on afterwards that has these problems on it. So I'm just going to go through the lecture part here, and then you can go and look at the problems, and that'll help. Okay. All right. When you're converting between English and the metric system, and again, in science, we don't do conversions because we don't have to, but 1 inch is 2.54 centimeters. Okay, that's the exact conversion. Okay, 1 mile is 1.609 kilometers. If you ever go up to Canada and it says you can go 88 kilometers per hour, and you're thinking, yeah, no, that's about 55 miles an hour, you guys, so be careful. An inch, a meter is 39.37 inches, so it's a little bit more than a yard. Mass, we've got 2.2 pounds in a kilogram. So you can use these conversions. If you have English and you need to change it, you can use these conversions. Because remember, they're conversions, they equal 1. Okay? So if you're going to use dimensional analysis, let's say you're going to convert. All right, I have nutritional calories and joules, and I need to convert them. Okay? So here's my question. Where's my question? Oops, sorry. All right. So I have 15 calories and I want to know how many joules that is. Okay. So I start with what I know, 15 calories. Well, a big calorie is like a kilocalorie. So before I can change it to joules, I have to switch it to the little calorie. There's 1,000 little calories and 1 big calorie. This is a kilocalorie. I don't know why they do that. I don't know why they just don't write kilocalorie, but I think it's a food thing because I don't know. Anyway, I'm going to convert. First thing I'm going to do is going to take my 15 calories, 1 calorie on the bottom, 1,000 little calories on top. What I got rid was calories. Okay, this is a conversion factor as well. In every calorie, there's 4.184 joules. Okay, so I put joules here. And again, calories on the bottom, 1 calorie. I should have typed in 1 here. This should have a 1 and this should have a 1. Sorry, you guys. But what I did was I got rid of big calories, I got rid of little calories, and I got joules, and that's what I'm trying to do. I'm trying to convert big calories to little calories, and then calories into joules. So these are conversion factors. They're just like multiplying by 1. Okay, so I take this, and this is my answer that I get. Now I got to look at my answer because, see, this only has 2 significant figures. So I got to make sure my answer only has 2 significant figures. I can't write it as this. That's too many significant figures. So I rounded it to 63,000 and I didn't write a decimal. That would be, a close estimation of this, and then it would only have 2 significant figures. Okay, so that was the last thing I did. I adjusted my significant figures. Okay, when you use dimensional analysis, again, if you're going to convert calories to joules, you have to remember that 1 calorie is 4.184 joules. And again, these are conversion factors. You can just look them up in your book. You don't have to memorize them. Okay. If you're in the medical field, you have to do dosage, and dosage is also conversion factor. It might be mass. You might have to change something to milligrams. Or if it's volume, it might be, they say cc's, that's a cubic centimeter. That would be the unit of liquid. And they base it on the patient. You guys probably have gone through this. They'll look and see what you weigh, and then they'll convert how much medicine you're supposed to get. So those are conversion factors that are used all the time. Okay. Another conversion factor is density. Density is mass per unit volume. Okay. By that's how close are the little particles. Okay. If something has a density of less than 1, it floats. If it's greater than 1, it sinks. Okay. Here's another temperature. We in science, we use the Celsius scale. Again, that's the most common. But when we get our temperatures now, it's Fahrenheit. Okay, again, we're the only country that uses Fahrenheit. And the nice thing about Celsius, it's based on the freezing and boiling point of water. Water freezes at 0 and boils at 100. In the Fahrenheit, it freezes at 32 and it boils at 212. That's not a very uniform scale. Here's conversions right here. You can change Celsius to Fahrenheit. You take the Celsius scale, multiply by 1.8, add 32. If you want to find the Celsius and you have the Fahrenheit, you take Fahrenheit minus 32, divide by 1.8, and you get the Celsius. These are all conversion factors. When you see Kelvin, Kelvin is what they call the absolute scale. Kelvin, at 0 degrees Kelvin, everything is frozen. There is no movement. Hopefully we never get that cold. It's minus 273 degrees Celsius. Well, the nice thing about it is really easy to convert. If you have a Celsius temperature, just add 273 to it, and then you're in Kelvin. So they actually use the Kelvin scale because it's an absolute scale, but most of the time we just use Celsius. Another example to give you an idea, body temperature. Human body temperature, if it's 98.6, is 37 degrees Celsius. Okay, a nice day would be about 25. I know if you got up in the summer and they said it was 25 out, you'd be like, what? That's like in the 70s. That'd be a nice day. Okay, so this gives you the conversions. A Celsius degree is larger than a Fahrenheit, again, because it's a more uniform scale because we've got water freezing and boiling 0 to 100. Works out great. Okay, and again, that's what I was talking about with the Kelvin. Kelvin is the absolute scale, and it's down here. If you want to go from Celsius to Kelvin, add 273. If you want to go from Kelvin to Celsius, subtract 273. Don't worry about the 0.15. That's not a big deal. Okay? If you had me in 115 last chapter, when we did gas laws, we use all the gases. When you deal with gases, you have to deal with absolute temperatures, so that you use the 273. Everything else, you pretty much just use Celsius. Okay? Here's something called specific heat. Specific heat is the ability to hang on to heat. Okay? It's really important to us that water is excellent at hanging on to heat, because at night, water heats up during the day, and then at night at least lets some of the heat go, but it holds on to it really well so that we don't freeze to death. Because as soon as the sun came down, if we don't have water holding on to heat for us, we're going to die. Okay, so it's the measure of how much they can hold on to heat, and water is the best. You can see metals not so great, right? And again, heat travels through metals. That's why we have metal pans. We want the heat to travel through and get into our food. So metals that don't have very good water has really good specific heat. Okay, and that's that. So we are now done with our first chapter. And again, I'll put this PowerPoint without me babbling on there too, so you can go back and look up stuff if you need to.